This is lecture video 50, and we will cover a new integration technique in this lecture, which is called integration of rational functions by partial fractions. What does this partial fractions mean? So we will deal with quotients of polynomials like this. So we call such quotients as rational functions if we have both polynomials on numerator and denominator. And in this section, we try to express a rational function as a sum of simpler fractions. For example, like we did here. So this is a rational function, and we try to express it as a sum of simpler functions, which we call as its partial fractions. Okay. So while decomposing a rational function into its partial fractions, we will be following some certain steps. So we divide these steps into two main cases. First, where the denominator is a product of linear factors first, and then we will deal with the case where in the denominator we may have quadratic factors too. But before we start those cases, we need to first check something. So we will first look at the degrees of the denominator and numerator polynomial. If the degree of the f of x function is greater than or equal to the degree of g of x, you need to perform a polynomial division first. And then once you have this degree less than the degree of the denominator, you can apply partial fractions technique, okay? So you need to first check the degrees. If the degree on the numerator is bigger than or equal to the degree at the denominator, please first perform a polynomial division, and then you will end up with such degrees. Then you are allowed to apply partial fractions technique. So let me describe the steps given in your course book like this. So let me try to explain them in a simpler way. So first, if the function at the denominator g of x is a product of linear factors, then, for example, like this is an example of two linear factors. So by the way, what's a linear factor? Linear factor are the factors of this form where you have degree 1, ax plus b, a and b can be anything, where a and b are real numbers. A is a real number, b is a real number here. So we want to decompose this quotient into simpler partial fractions like this. So you can write it like this. You can just decompose it into two factors like that. What if g of x function at the denominator contains repeated linear factors? For example, x plus 1 to the power cube. This is a repeated linear factor. Then you pretty much apply a similar decomposition like we did here. For example, you also have x minus 2, x plus 4. These two are still linear factors, and for them, you put some constants and write them as partial fractions like this. So how we handle the repeated part? So you keep writing the partial fractions like this, and at each new step, you need to increase the degree by 1 till you reach the degree given here, okay? So you keep writing x plus 1 squared, x plus 1 to the power 3, and you need to do that till you reach the actual power given here. So cube, so I stop here. And for all of these denominators, you need to put a arbitrary constant ABC at the numerator part. Okay, that's what you should do if denominator contains repeated linear factors. Okay, let's look at the main case too. Okay, so in this box, we look at the denominator and we allow quadratic factors happen. So what if g of x contains quadratic factors? What does a quadratic factor mean? So it is a polynomial of degree 2, which is irreducible. Irreducible means you cannot decompose it anymore into its linear factors. So x squared bx plus c, if it is irreducible, the discriminant, remember what was the discriminant? It is b squared plus 4a minus 4ac. If this is less than 0, it means that this degree 2 polynomial is irreducible. You cannot decompose it anymore, so there are no real roots. That's why you need to leave as it is. So it is a polynomial of degree 2, which we call as a quadratic factor. So for such factors, instead of just putting c on the upstairs, you need to put ax plus b form, okay? Not just a, for example. You always put one less degree to the denominator. You see, this is degree 2 and you put one less degree. That's why you need to put ax plus b form here. Okay, and the last case is when the denominator contains repeated quadratic factors like this one here. So you know what you should do when it is repeated. You keep writing it with the rule applied at the denominator till you reach the exact power given in the denominator here. Okay, so I keep writing it to the power 1, to the power 2, and then I also need to obey the rule that I should apply for denominator ax plus b, cx plus d, because these are quadratic factors. And for the last factor here, which is a linear factor, okay, this is a linear, so I apply the rule for the linear factor, which is just putting a constant on the denominator part. Okay, so this is the summary of the strategy that you need to follow to decompose a rational function into its partial fractions like this. Okay, let's start with the first example. We want to integrate this, and let's look at the denominator and try to see whether it is a product of linear factors, whether it contains a quadratic factors, is there anything repeated? So let's try to understand that. So it can be decomposed into two linear factors like this, obviously. And then now I need to find its partial fractions. I need to express it as a sum of simpler fractions now. Okay, so, and first thing to notice is that the denominator is a product of linear factors. That's why, how do I decompose it? Okay, this is a linear factor, that's why I just put a constant to the denominator. This is another linear factor, and I need to put another constant to the upstairs. This is the rule for the rule when we have linear factors. Okay, then let's try to find a and b. How can we find them? If we expand the denominators on the right-hand side, like I need to expand x minus 1 with x minus 1, and I need to expand with x minus 2 here, then what do I obtain? I got a times x minus 1 plus b times x minus 2. This should be the same as the denominator on the left-hand side, okay? So this should be the same as this. And then you can insert the roots of these linear factors to solve for a and b, of course. If you insert x equals 1, then what you have, this part is gone because it is multiplied with 0. And this is, for this part, if you insert x equals 1, you obtain minus b. Insert x equals 1, you got minus 2. That's why you solve b as 2. And then you insert the other root, which is 2. Then this part is 0. Insert 2 here, you got a. So insert 2 on the right-hand side, and you got 3. Okay, we easily find the coefficients a and b like this, and then we are ready to integrate the given integral. So this was the original question. What I did, we decomposed it into its partial fractions. So it is like this, a over x minus 2 plus b over x minus 1 dx, and we solved for a and b. A is 3, b is 2. That's why this integral is in fact the integral of 3 times x minus 2 dx plus the integral of 2 over, not times over, sorry, dx. And these are very simple things to integrate because 3 is a constant, 2 is a constant, integral of dx over x minus 2 is ln x minus 2, you know? So x minus 2 plus 2 goes out, and similarly ln absolute sine of x minus 1. Since these are indefinite integrals, you need to add an arbitrary constant c at the end. Why do I integrate this as ln? Because, let me put here quickly. So if you call or name this as u, then this part is exactly du. Then your integral becomes du over u, which should be integrated ln absolute sine of u, where u is x minus 2, right? Okay, so let's move on with the next example now. Okay, this time we again have a denominator that's a product of linear factors, you know. But this is a denominator consisting of linear factors. Once you notice this, you understand how to decompose it into its partial fractions, like this one, and this one. Since all the factors are linear, you just insert a, b, c constants for the denominators. Now, our aim is to find these constants. What are they? How can we find them? Of course, by expanding the denominators here and then multiplying them with a, b, c, equating it to the denominator on the left-hand side, and then we try to solve the constants. So I need to expand with x plus, what is, okay, you should think like, what is missing here to reach this common factor? So it is common multiple. So like this, you need to expand because look at the denominator. These two are missing for the first term, and for the second term, this is and this is missing. For the last term, you need to expand it with these two. And then you see x plus 1, x plus 3 is multiplied with a, x minus 1, x plus 3, x minus 1, x plus 1. So I multiply them like this, and this should be the same denominator given on in the left-hand side. And then you will do all these multiplications, okay? Do all the multiplications and arrange your terms now according to x squared, x, and the constant terms. Okay, this is the nicer version of the right-hand side. And after this step, you need to compare the coefficients of the same degree terms. Like, what do I mean? Okay, so the coefficient of the x squared on the left-hand side is 1. What is the coefficient of the x squared on the right-hand side? It is here. That's why this should be what? This should be 1. So just compare the coefficients of the same degree terms on the right and left. Next, what is the coefficient of x on the left? It is 4, and it corresponds to here. That's why this should be 4. And one more coefficient we have. Okay, the constant term is plus 1. Okay, maybe. So the constant term is plus 1, and it should be the same constant term on the right-hand side. That's why this should be 1, okay? So this is 1, this is 4, and the constant term should be 1. If you solve this system, you can find the unknown coefficients. So solve the system. Okay, how you can solve it? You can use your linear algebra skills to solve it. Or there is this second way to find the coefficients here. Let's call this as the first way. Or you can follow the second way. So this is the equation that we have here, right? And you, instead of doing all the computation and comparing the coefficients of x squared, x1 and constant term and solving the system, instead of this way, you can start inserting the roots, okay? Insert the roots. So the first root is x equals -1, right? If you insert it like this, like this, like this, these are the different roots coming from the linear factors. If you insert x equals -1, so let me write better here. So what you obtain, if you insert x equals -1, so this will be gone, this will be gone, then the only middle term will survive. So it will give you -4b equals, you will also insert -1 to the right-hand side. Equals -2, because insert -1, then b is solved as 1/2. Insert -3, then on the left-hand side, you obtain 8c. -3, -3, these two are gone, this term will survive. And you have this equation then, -2. And insert -3 also right-hand side, which will give you -2. And then c will be solved as -1/4. And finally, insert x equals 1 to solve for a. So you will obtain 8a if you insert x equals 1 on the left-hand side. Right-hand side will be 6 if you insert 1. So a is solved as 3/4. Okay, these are your coefficients now. And now I think we are ready to integrate the given example. So integral was looking like this. For x plus 1 divided by x minus 1, x plus 1, okay. So x minus 1, x plus 1, and x plus 3 dx. What did we do? Remember, we tried to decompose this rational function into its partial fractions, which are simpler to integrate. A, B, C are solved. So it is a over x minus 1 plus b over x plus 1 plus c over x plus 3, where a is solved as 3/4 and b is solved as 1/2 and c is -1/4. Right? And then you can integrate from right-hand side easily. These are all ln functions after the integration. So 3/4 is just a constant in front, ln x minus 1. 1/2 is just a constant. Okay. ln x plus 1 minus 1/4 is constant, it goes out, and it is ln this plus an arbitrary constant c. So that's how you should handle an integral of rational function whose denominator consists of linear factors. Okay, let's look at another case now where the denominator consists of repeated linear factor. You see, it is a repeated one. So let's write this down. This is a repeated linear factor. Please don't consider it as a quadratic factor, because even if the degree is 2 here, it can be decomposed into its linear factors, which are both x plus 2 times x plus 2. So it is not quadratic, it is reducible, but a repeated linear factor. Okay, how do you decompose it? This is your rational function. The rule is you keep writing the same factor till you reach the exact power given on the question. Okay, this is your partial fraction decomposition, and then you need to start expanding things on the right to find the coefficients a and b. So what you obtain here, you got a times x plus 2 plus b is, it should be the same as 6x plus 7. Okay, then you can try inserting the roots. X equals minus 2 will make this part 0. So directly you can solve b as minus 5, right? Okay, and then how to solve a? Since there is no linear factor here, there is no root that I can insert, but you can insert this known information. Now b is minus 5, right? Then what you obtain, a, okay, let me write another color, insert this, b equals minus 5 equality into your equation. So b equals minus 5, 6x plus 7, and then you can do the multiplications. Ax plus 2a minus 5 is this. Now you can compare the coefficients. So you see coefficients of 6 is, x is 6, and you have a here, which shows that a should be 6, okay? Then, with these coefficients, now a is 6, b is minus 5, you can easily integrate the given rational function. It was like that, the question, and then we decompose it into its linear, into its partial fractions, where we have a repeated linear factor at the denominator. So the coefficient a is solved as 6, coefficient b is solved as minus 5. Okay, let's evaluate the integrals. 6 goes out, this, okay, you have dx everywhere. This is ln absolute sine x plus 2. How do you integrate the second integral? Let's do it here. It is minus 5 over x plus 2 squared dx. So if you choose this part as u, so what you obtain, u is x plus 2, then du is dx, then the integral becomes du. dx is exactly du, and this is u squared, right? And you can integrate it as a power function like this. So the integral is add 1 to the power, divide by the same power. That's why the result is just 5 over u, where u is x plus 2, right? Okay, that's why the second integral is just 5 over x plus 2. And don't forget to add this arbitrary constancy because it is an indefinite integral. Okay, so I think I will stop here for this lecture video. Maybe let me see the next example. Yes, we can also cover this one. Look at the example. So you have x cubed and x squared. So the degree of denominator polynomial, degree of f of x is, which is 3, is bigger than the degree of the denominator polynomial, which is 2. If this happens, you have to perform a polynomial division, remember? Before trying to decompose your rational function into its partial fractions, you need to do first the polynomial division. Okay, it is 2 x cubed is minus 3 divided by x squared, like that. Okay, if you do this polynomial division, you need to multiply it with 2x squared, and then what you have, 2x cubed minus 4x squared, 3 minus 6x. So you have what? Then here you will get 5x. So minus minus plus 5x minus 3. Okay, then the division is over, which means that you can write this rational function as this part. Okay, this is the result. Then the remainder comes here. divided by this same polynomial. Okay, now if you check the degrees, degree of the numerator is less than the degree of the denominator. Okay, degree is 1 and the degree of the denominator is 2. This is less than. Then you can start applying partial fractions method. So to integrate this whole thing, you need to understand this part. 5x minus 3, x squared minus 2x minus 3. Okay, look at the denominator. This denominator can be written as x minus 2 and x plus 1. That's why you can decompose it as a over x minus 3 plus b over x plus 1. And if you do these expansions and multiply like that, you can easily solve for a and b. So from here, a is solved as 3 and b is solved as 2. If you insert the roots, of course, if you insert x equals minus 1, you solve, if you insert x equals 3, you solve for a. And if you insert x equals minus 1, you solve for b. And after solving them, this thing is much more easier to integrate. So what was the original question? Integral of this. Instead of integrating it with this form, we will integrate it on the right-hand side. So the question is integrating this thing. X squared minus 2x minus 3. So this is what? Integral of this. From here, we will integrate. A is solved as 3 and b is solved as 2 dx. Now you can integrate term by term. Integral of 2x is 2x squared over 2 plus 3 is just a constant times ln x minus 3. 2 is just a constant, ln x plus 1 plus an arbitrary constant c. This is your result. So don't forget to check the degrees. If the degree of the denominator is bigger or equal than the degree of the denominator, you have to perform a polynomial division first. And then you can apply this part, your partial fractions techniques, because now degree is as you wish. I stop here.